Okay, so now we're trying to make the application range a little bit broader. So just let's assume the thickness of each layer is arbitrary. It's a arbitrary given thickness, arbitrary thickness like L1 and L2. But the rule is the same. It is repeating itself in one pair, and like since it is still a reciprocal system, so the property of the eigenvalue can be still written in this way. So exponential Kc will be half of T11 plus T22 plus square root and blah 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 blah, just like this one. So the final reflectivity can be of ampere. The overall reflectivity after ampere can be directly deduced from the result of the transmission matrix of the one pair. Yeah, since if you have the T1P, T1P is equal to T11, T12, T and 21, T22. You have these four elements then you can have its Kc. Then with ampere, basically you can directly be calculated, or although the form how it looks is not so elegant. It looks like a little bit complicated, but let's see how we obtained this result. Okay, so again we repeated the property with like the interface is a 4 segment, like the 4 segment with first interface homogeneous median, second interface second homogeneous median, and we just do the brutal work. You probably you can try to do that by yourself. It's just trying to do the multiplication of 4 matrices is a little bit tedious, but not that difficult. Anyway, the final T11, T12, T21, each element can be written in this way. So T11 will be 1 over T squared divided by exponential I phi plus, and the phi plus is the beta 1 L1 plus beta 2 L2. And it also has the second term minus R squared E minus I phi minus. So the phi minus is the beta 1 L1 minus beta 2 L2. Okay, and the beta is the 2 pi k divided by lambda. If the layer is not transparent, probably you have a you will get a imaginary term, but in current stage we just assume there's no such term. Yeah, but probably next week we will see what happens if we have an imaginary term. Okay, so you have the T11, T12, T21, and T22. Yeah, and with such T1, then you can substitute into this relation to obtain your Kc, although the expression is not so clean, but basically it can be calculated. Alright, so the same, and since we know that its eigenvector and is invariant. If it is an eigenvector for one pair, it is the eigenvector for n pair. So we still write the two equations like this. This is the eigenpair, for one pair, the equation from one pair, and the second part is the eigenvector from and the relation based on the n pair. Okay, n pairs. Okay, it's basically just identical with the result we have where, yeah, we have let's see, I think we already deduced that. Yeah, it is here. Yeah, okay. So it is just the replica of this equation in slide A. Okay, so let's continue. Alright, so you have actually 4 useful equations. It is 1, 2, 3, and 4. Okay, so the whole procedure is looked like this. It is a little bit painful, and probably you can just like take a pause and see how does this get, and I will just run through the procedure. So first, this is according to the first equation. We can write it down like T12 times. Okay, this T12 times this T exponential plus m echelon m c minus TG11. The TG11 means is the T11 matrix element of the grating. Yeah, since we are trying to find the matrix element of the whole grating. Okay, so and it should be equal to exponential plus. We're only taking the plus term times the TG12. Okay, so this is the first equation. Second, we repeat the same thing for the minus eigenvectors. Alright, so we also get the equation like here. So we call this is the equation 1 and this is the equation 2. So first we can do a subtraction between 1 and 2. Then we can eliminate the T11 here. So that will be T12 and times exponential m c minus exponential minus m c. And the right hand side is exponential c minus exponential minus c. Okay, TG12. So the TG12 can be written down like this after rearrangement, and we can divide the 2 on both sides. So it becomes the hypersine m c divided by hypersine c times the T12 element of the matrix for one pair pair structure. Then we can also try to divide 1 with 2. Then we can eliminate the T12 and the TG12. Then we have the relation like this. Okay, so yeah, we're trying to repeat the similar stuff to times it to and equate both. Then do a sequential rearrangement. Then we put the TG11 to one side and the TG1 to the other side. Then we finally get that the TG11 could be hypersine m c divided by hypersine c T11 minus an additional term, which is hypersine m minus 1 c divided by hypersine c. The m is the number of pairs. So if there's only one pair, though, the second term goes to 0. So which this is reasonable. Then TG11 will be equal to T11. Alright, so now we have the relation of the TG12 to T12. Yeah, so if we have the matrix element T12, we can have the matrix element of the whole grating. Yeah, after turning it up m times, so you can get the matrix element. And similarly for TG11. And here comes the second course that you take for the second row. yeah, you do the second row and repeat that again. Okay, so you also build the relation between TG21 and the TG21, TG21 and the T21 and the TG22 and the T22. All right, so if you have one pair T1P, one pair is and T11, T12, T21, T22. Alright, and the T grating is equal to T1 pair times M times, and is equal to TG11, TG12, TG21, TG22. Okay, so as long as you have this matrix and know how paired it is, you can directly access this 4 element with the 4 element founded for the one pair case. Okay, so with such relation, we can still find the reflectivity of such pair by TG21 and the TG11. Alright, so since we have the TG like this one, so we can write out the matrix like this. This is the A, B is equal to TG11, TG12, TG21, and TG22. Yeah, and that input to be A0 and 0. Okay, so that means you, after alternating source powers, you have the A here and the B here, but you only have output power A here, but the input is 0. So if we simply see the matrix like this way, so we can find it will be TG11 and the TG21 times A. Okay, so the reflectivity will be, it should be B over A for this case. So it will be TG21 over TG11. Okay, so then you put these two equations. Yeah, the result here goes to here. So finally get the still a little bit cleaner, but still a little bit difficult to solve. But anyway, we have the expression for the reflectivity of an arbitrary grating, not necessarily on the Bragg's condition. Okay, let's take a break.